So before we begin to evaluate exponential expressions, let's revisit the definition of an exponential expression. So I'm going to give you two functions. F of x equals x squared, and g of x equals 2 to the x power. So at first glance, these seem to be similar functions, or similar enough. But at closer inspection, we see that f of x is really just a power function. We have dealt with these for years. We know exactly how to graph this. We know how to translate it. We know how to factor higher order forms of them. We know how to work with these. But this second function, g of x, where 2 is the base and x is in the position of power, or in the power position, this is called altogether an exponential function. And what you're going to find is that exponentials can't be solved using basic algebra. They're called transcendental functions because they transcend basic algebra or algebraic calculations. So this entire unit will deal itself with solving exponential functions and their inverses. So let's get started. First, let's formally define an exponential function. P equals ab to the q. So a couple of things. 1, that's a percent, q. So 1 is, when I'm writing the formula for exponentials, I don't like to use x's and y's because later, when you're trying to use the formula to understand actual functions, sometimes it can get confusing whether you're talking about an x or a y from the function or an x or a y from the definition or the formula. So I use p's and q's when I'm talking about the formula, and you're welcome to use x's and y's, but when you're learning I kind of don't recommend it, but whatever you want to do. So f of x, p is in the position of f of x or y. So that's what we're talking about. We're looking for a function, an exponential expression on the right-hand side with an equal sign means we're dealing with a function. So the f of x or y, q is in the position of the variable, generally x in this case, and a is a real number not equal to 0. And the reason for that is a is really just the squeeze or stretch on the parent. We remember from working with parent graphs. And if a equals 0, then b to the q disappears, and we're not dealing with an exponential function at all because 0 times anything is 0. And b is the base. And for an exponential function, the base has to be a real number, positive real number, and also not equal to 1. And the reason for that is if 1 to any power is just 1 times a, it's just a horizontal line. So let's try to understand what these functions are, and we know whenever we deal with functions like this, we always try to understand them by looking at a picture, and for us a picture is a graph. So let's head over to Desmos and have a look at the graph. So here you can see I've set up y equals b to the x. That would be a general function. I didn't put an a in because a is just squeeze, stretch, flip. And we want to look at what happens to the fundamental form. So y equals b to the x, where b equals 0. You can see that I have a horizontal line on the x-axis, and the reason for that should be obvious. If b equals 0, it doesn't matter what x is, the output is always going to be 0. And negative inputs of x aren't included because if I had a negative x value, that would be the same. This function would be y equals 1 over, remember a negative exponent puts it into the denominator, 1 over b to a power, and if b is 0, you can't ever have 0 in the denominator. So the function doesn't live here. So let's look and see what happens if I have a 1. So 1 just gives me a horizontal line. Same reason as before when b was 0. It doesn't matter what the input is how 1 to any power is going to equal 1. The only difference is now I don't have a 0 in the denominator issue. Excuse me, had to take a phone call. So now I'm going to set my graph in motion. So as my b values change, notice negative b values don't exist, right? The whole graph doesn't show. But didn't we already define that an exponential function is only defined if b values are positive and not equal to 1? So let's put it back into motion. You can see we're coming up on the 0 position as we expected. We get that, a line. And then we get the same curve, only a slightly different shape. And if you watch, and I'll stop it at various positions, let's let it move to b equals 2 and stop it. All right, so when b equals 2, we get the y-intercept we expected at 0, 1, but we also get the output of 1, 2. When I put in 1, I get 2. And so this would be the shape when the base equals 2. But if I change the base, even by 1 or by a tiny little bit, suddenly now the graph intersects at y equals 3. Or excuse me, the input 1 produces an output of 3. Change the base again, and I get a point where the input 1 produces the output of 4. And so the graph changes depending on the input. The shape of the graph changes depending on the input. Let me put them all on. And let me turn off all of the numbers. Okay, and watch what happens. So see, depending on what the base is, we get a different shape to the graph. All right, that's enough of that. So let's look at some of the translations that can happen with this graph. First, let's notice what happens if our variable or our power is negative compared to when our power is positive. So what we just looked at was all input values of x that were positive. And if the base is greater than 1 or 0, we get a curve that looks like this. Remembering, I'm not going to label it just for neatness, but this has to be y equals 1. And we looked at what happens to points on the right-hand side of the y-axis, but what happens on the left-hand side of the y-axis? Well, we're definitely going to get an asymptoted 0 because there's no value that I could plug in for x. So in this case, let's say we're going to use x's and y's. Y equals some base b to the x. There's no x value that I could ever plug in to create a 0, because if I chose 0 for x, I get 1. There's no x value that I could ever choose to create a 0 value. And because b is always positive, I'm never going to cross over the line. So the x-axis becomes an asymptote for the exponential function. And notice that as I choose x values to the left of y, of the y-axis, my x values become negative. So for example, y equals b to the minus 2 is really just y equals 1 over b squared. That's just a fraction, and the bigger and bigger and bigger negative I get, the bigger and bigger my denominator gets, so the smaller and smaller my number value gets. And I just approach but never touch the x-axis. And that concept leads us right to our next picture, is what happens if I'm looking at y equals b to the negative x. In this case, I'm going to take the opposite of all of my x inputs. So if I choose a positive x, the function itself is going to convert that positive x value to a negative, and this is what's going to happen here, the same thing that happened. So my graph is still going to cross the y-axis at 1, because turning negative x into 0 is just negative 0 is the same as 0, but my smaller and smaller values are going to be on the right-hand side, and my bigger and bigger values will be on the left-hand side. Choosing negative 2 on this graph will turn into, well, b to the negative 2 is b squared, so I get bigger and bigger on this this side. So this is a general function, a general rule. Y equals b to the x has this parent shape where you have a graphing point of y equals 1 and 1 whatever b is, and the other shape would be y equals b to the minus x, where you have again the same graphing point at y equals 1, and your second graphing point for the input of 1 is 1 over whatever your b is, your base is. All the rest of the translations work exactly the same, so let's do an example to see that that's true. So let's graph f of x equals minus 3x to the minus x plus 2. Egads! What are we going to do now? Okay, well, let's look at the parent first. Let's kind of just break this down and look at the parent first. We know the shape of the parent. Whoop, we don't. We know that the parent is a negative x. So we're looking at y equals b to the negative x. So we know the parent looks like this. Right? Where this is 1, and this point is 1 and 1 over b. Okay, but what is b? Well, b is, oh wait, I wrote it wrong, I'm very sorry. There we go. That must have confused you, apologies. So where was I? Oh, b equals 3. So I can say that another graphing point is at 1 and 1/3. So that's just the parent. That's doing nothing else to the function. But look what I have. Y equals a times the f of x minus h plus k. This is what we use to graph our translations. Well, I clearly have my parent, because I'm dealing with minus x as my parent, plus 2 is connected to the x, right? So x minus h, remember x is cattywampus, so I'm going to move backward 2 units, and then this negative 1 in the front says, I'm just going to flip it over the y-axis. So I'm not squeezing or stretching, I'm not making it bigger or fatter or doing anything else, all I'm doing is flipping it. So that means my 1 is going to flip down to my negative 1, but it has to move backward 2. So it comes back 2. So let me take that first one out. So my 1, my point 0, 1 has flipped to 0, negative 1 and gone backward 2, which puts me at negative 2, negative 1. Well, let's graph it here. Negative 2, negative 1. And then my 1/3 point is going to flip over. Luckily, that one's kind of easy to do as far as the 1/3, the output part, but I just have to back up 2. So I'm going to flip over and back up 2, which takes me to negative 1 and negative 1/3. And now if I graph this, oh, I labeled my points right in my way. It does that without actually touching the x-axis. Let's see if I can erase that. Yep. Okay, so I've graphed. No big deal. The only difference at this point of the game is remembering that the shape changes depending on the base, and we have the added, if there's a negative exponent, it becomes this shape model, which is we've used before as exponential decay. So that's the exponential decay model, and the first form is the exponential growth model. And one last thing before I let you go, something you've definitely seen before, though not necessarily seen it in this context, and that is the base e. The base of e. So e is a number like pi. It's an irrational number. As far as we know, we've never discovered the in or the point after which it repeats, but it's just a number. So e has a value of 2.718 And then it goes on and on and on like pi. We tend to round it to 2.718 rather than 2.72. That's too much of a roundup. And we call this the natural base. And the reason we call it the natural base is this isn't a number this number is like pi. We didn't make it up to make our lives convenient. It shows up. So when scientists are discovering the world around us, the number E, or the natural base, shows up all the time. It's like the number of fingers that God has. Our base, we work in base 10 because we have 10 fingers and 10 toes, and whatever forces created the universe apparently has E fingers and E toes, because that's the base we work in, or that the nature works in. So the graph, if y equals e to the x, looks exactly the same, except it crosses at the y-axis at 1, and it has a graphing point of input 1, output e. Same thing, the graph of y equals e to the negative x, this would be y equals e to the negative x, has an y-intercept at 1 and a graphing point at input x, output 1 over e. So nothing's different, it's just a different base, and we will make a lot of use of that base.